The Levinson-Durbin algorithm is used frequently for solving a system of equations as we encountered with ARMA modeling. When we have a system that effectively is a solution to this problem, as we had before, minus Rx, where we have the structure of a Toeplitz matrix, then Levinson-Durbin algorithm is used. So your cell phones are doing this every time you make a phone call, literally hundreds of times per second. But it also has application in many other areas. So as a reminder, we will define R for our purposes, although it will work for any similar matrix, as a data matrix where we have each defined as Rx is equal to xq Hermitian. If it's real, of course, you can just use a transpose, q plus 1, where xq is made up of data samples, xq, xq minus 1, to xq minus p plus 1. And then each row is advanced relative to the previous row. So this will be xq up to xq minus p plus 2, xq plus 2, xq plus 1, and so on. We've also defined this vector vector q plus 1 refers to the very first element of the vector, so that's little x q plus 1, x q plus 2, and so on. So with this context, we're actually going to frame the problem a little bit differently as we start developing the Levinson-Durbin algorithm, and then we'll work our way back. So with Levinson-Durbin algorithm, we're going to use a system where we have a matrix H, a little bit change in notation here for reasons that will become apparent in a minute, times V is equal to Y, and H will be defined like so, and you can see that since if we're dealing with a real matrix, this is symmetric. If it's complex, we would put our little conjugate markers in there, and it would be Hermitian. And we're going to start with y equal to little h, a vector where little h is defined as h1. Notice it doesn't start at h0. It starts at h1 up to hn. Okay, before we get too far, I want to do a little aside and talk about a type of matrix called the counter identity or exchange matrix. This will be really useful as we move forward, just in notation and everything else. So J is going to be the matrix that looks like we took an identity matrix and flipped it left right or up down. So this matrix reverses entries in a matrix or vector that it multiplies. So if x is equal to 1, 2, 3, then j times x is equal to 3, 2, 1. Well, because of that, j times j is just going to be the identity matrix. Also, we can see that j is symmetric, so j transpose is equal to j. And when we're multiplying matrices, j times the matrix does to each column as it did to x. It reverses it. And a matrix times j reverses the rows. Okay, now that we've got that little aside out of the way, let's see what it does to our symmetric tuplets matrix H. So if we have j times h, then we're reversing each of the columns, which will look like this. To h0, this will be h n minus 2, all the way up to h0 at this point. So we used to have h0 on the diagonal, and now h0 is sitting on this, I don't know what it's called, cross diagonal, I guess. So h1 to hn minus 1, h1, and so on. And then, of course, because it's tuplets and it has all this structure, if we do j, h, j, we reverse the columns and we reverse the rows. Well, we can do this. Let's see. h0, h1, hn minus 2, hn minus 1 for that row. We reverse the second row, and it looks like this. All the way down to hn minus 1, h0. As we flip these around, this would be h1. So this is now just back equal to h again. So to tie all these together, we have h is equal to j, h, j. And we can multiply on the left by j, giving us jh is equal to hj. And h inverse, then using our identity up above, it's going to be that inverse, which would be j inverse, h inverse, j inverse. We reverse the order, but it's a palindrome anyway, so it doesn't really matter. We found that j times j is equal to I, so j is its own inverse. Therefore, this is j h inverse j. So we get the same property here, which is that h inverse times j is equal to j times h inverse. Okay, Now we can bring this all together, and we'll take our H matrix and we're going to divide it into several submatrices. So H0, H1, and so on. This last row, or column rather, Hn minus 1, Hn minus 2, down to H1, H0. We're going to have now Hn minus 1, Hn minus 2, down to H1 and H0. So we're going to partition this matrix in this manner. And as we operate on our equation here, V1, V2, Vn minus 1, we'll partition this to Vn. And we're having so much fun doing this partitioning, we'll do it again over here. H1, H2, down to Hn minus 1, and Hn. And we'll partition that matrix too. This will give us, we're going to call this the matrix Hn minus 1. This is J times the vector Hn minus 1. That's just a scalar H0. And then this is the same thing as we had in the right column, but now it's a row. So we'll transpose it and go there. Now labeling each of these entries, we just call that Z and that beta. Z is a vector, beta is a scalar, and now we have H n minus 1. Oh, that's nice. We've seen that before. Hn. I guess we should probably make sure that we're all clear as to what Hn minus 1 is. Hn minus 1 is H1 up to Hn minus 1. And this, of course, shows up in 3 different places. Okay, so far I've just been showing you a whole lot of things without motivation. Let's talk a little bit about where we're going, and hopefully it'll be useful to help you orient to what's going on. The basic idea is that we're going to try to solve this problem. We're solving for Z and beta, but we're hoping to do this by assuming that we have the n minus 1th order problem solved, and then we want to just do a simple update to solve the nth order problem. And if we have some kind of a structure like this, then we can go back and do it recursively. Start with a trivial 1-by-1 problem and grow a solution that's a little more efficient. Okay, so once again, overall, we want to solve for Z and beta. So we can now take our partitioned matrix equation and write things out. From the upper left partition, we have Hn minus 1. That will be multiplying Z. And then we have plus j h n minus 1 multiplying beta, and that will be equal to h n minus 1. Likewise, we can solve the bottom part, and we note that j times h quantity transpose is just going to be h n minus 1 transpose times j. We just reverse the order. That'll be multiplying z. And then we have plus h naught beta, and that will be equal to h of n. So let's take this top equation and solve for z in this one, and we get z is equal to h n minus 1 inverse times h n minus 1 minus j h n minus 1 beta. And expanding that out gives us h n minus 1 inverse h n minus 1 we can multiply all this through. Okay, first, how did I get to that step? As you recall, j and h and j and h inverse commute. So when we multiplied that through, we commute. And of course, a scalar commutes with a vector and a matrix. So that works out there. Okay, here's the big step. Suppose that we already knew v n minus 1 is equal to h inverse n minus 1 h n minus 1. So in other words, we've just given it a name, but we're saying, what happens if we already know this? It shows up in a few places. Then we would have, from our equation that we've just developed for z, we would have z is equal to our newfound v n minus 1 minus beta j v n minus 1. So, using this with this equation that we haven't forgotten about, I hope, yields h transpose j z from our start equation, and now we put in our expression for z in terms of things that we postulate we know, minus oops, not minus, plus h naught beta is equal to h of n. And so we can solve for beta as beta is equal to this nice little equation here, which h transpose n minus 1 v n minus 1. Great. Now, this is important enough to circle, but it's not yet our complete solution, so we won't do it in red. Okay, it's important to take stock right here and notice that this is essentially the solution to the problem of order n minus 1 instead of order n. So up here, and we might do well to put this here. This is h of n is equal to, and here we have v of n. Oh, I'm sorry, that's not an equals, that's a times. Times v of n is equal to little h of n. And we've solved that problem. So here in this, where we've marked it in orange, this is really the solution to the smaller problem. When we have that solution, we can now, and now we have our beta, we can now get our v of n is equal to z, which is given above, augmented by beta, and just iterate the point, h of n. So given the solution to this smaller problem, we can find the solution to one step larger in on time. On comes from the fact that this is basically a vector inner product, which is O n minus 1. We have another vector inner product, also n minus 1 operations, and then a scalar division. So it's approximately On time. So now the whole solution to this simplified problem, we still have a step to go beyond this, is to first solve h1 v1 is equal to h1. This right here is a 1 by 1 system. So it's a simple division. Then we use that to solve h2, and now we have a vector v2 is equal to h2. This is a 2 by 2 system. All the way down, and we do h3 and v3 and so on and so forth until we finally get to hn vn is equal to hn. So what's our total cost? Well, it's going to be some constant times 1 plus 2 plus n And so that's ON squared. To put that in context, ON squared is also the complexity of a simple matrix multiplication. So we can actually solve this matrix equation with about on the same order of complexity as doing a matrix multiplication. This is a fantastic tool. Okay, so what do we have to do next? Well, as you may recall, the first thing we did is we said let's start with y is equal to h. So we have h times v, and v is what we're solving for, is equal to h. So we have our little h's on the left-hand side and on the right-hand side, but we would like something a little more general. We'd like to go back to the y case, and so that'll be in the next lecture.